On the morning of October 25, 1944, in a cramped metallurgical laboratory beneath the Kure Naval Arsenal, Chief Metallurgist Takeo Yamamoto held a fragment of American naval shell casing under the harsh glare of laboratory lights. The jagged piece of metal, still bearing scorch marks from its violent entry through the deck plating of the battleship Musashi, felt impossibly heavy in his trembling hands. His team of 6 engineers crowded around the examination table, their faces reflecting equal parts scientific curiosity and something darker, something they could not yet name. They believed they were about to confirm what Japanese naval doctrine had proclaimed for years, that their superior metallurgical techniques and warrior spirit had produced armor plate unmatched anywhere in the world. They could not have been more catastrophically wrong. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What these Japanese metallurgists were about to discover would shatter not just their professional confidence, but the very foundation of their nation's naval strategy, revealing an industrial gap so vast that no amount of courage or sacrifice could bridge it. Yamamoto had served the Imperial Japanese Navy for 17 years, rising through the ranks to become one of the most respected materials scientists in the entire naval establishment. He had studied metallurgy at Tokyo Imperial University, where he had written his doctoral thesis on the crystalline structure of hardened steel alloys. His work had contributed directly to the development of the armor plate used on Japan's newest battleships, including the massive Yamato and Musashi, which displaced over 70,000 tons each and carried armor belts up to 16 inches thick. The Japanese had convinced themselves that their vertical armor system, combined with horizontal deck armor designed to defeat plunging shell fire at long ranges, represented the pinnacle of naval engineering. Yamamoto himself had overseen tensile strength tests that showed Japanese armor plate could withstand impacts of up to 45,000 pounds per square inch. The numbers had seemed irrefutable. The fragment on his table had been recovered 3 days earlier from the wreckage of Musashi after the battleship had endured a devastating attack by American carrier aircraft in the Sibuyan Sea. The great ship had absorbed an incredible amount of punishment, hit by an estimated 19 torpedoes and 17 armor-piercing projectiles, before finally capsizing and sinking with over 1,000 crew members still aboard. Naval recovery teams, working in hazardous conditions, had managed to retrieve several fragments of American ordnance that had penetrated the ship's armor. These fragments were now the subject of intense scrutiny, as Japanese naval authorities desperately tried to understand how their most powerful warship had been overwhelmed so completely. Yamamoto's assistant, junior engineer Hiroshi Nakamura, carefully positioned the fragment under the laboratory's most powerful microscope. Nakamura was 26 years old, a brilliant young scientist who had graduated top of his class from Osaka University. He had joined the Naval Research Program, believing that Japanese industrial might would ultimately prevail through superior technique and innovation. As he adjusted the microscope's focus, bringing the metal's grain structure into sharp relief, his breath caught in his throat. The steel's crystalline structure told a story that neither man wanted to believe. Under magnification, the grain boundaries revealed a level of refinement that exceeded anything in Japanese metallurgical practice. The alloy showed signs of a tempering process that produced exceptional hardness without brittleness, a combination that Japanese foundries had struggled for years to achieve. Even more troubling, the metal showed no signs of the stress fractures or inclusion defects that occasionally plagued Japanese armor-piercing shells. This was not the product of a nation supposedly running short of strategic materials. This was evidence of an industrial capacity operating at peak efficiency. Yamamoto moved to the spectrographic analysis station, where another team member, senior technician Kenji Sato, had been conducting elemental composition tests. Sato was a 42-year-old veteran of naval metallurgy who had worked on armor development since 1932. He handed Yamamoto a clipboard filled with densely packed numbers and chemical formulas. The composition readings showed trace elements and alloying ratios that spoke to a level of quality control the Japanese could barely imagine. The nickel content alone suggested access to virtually unlimited strategic resources. Japan, by contrast, had been forced to reduce the nickel content in its own armor plate by nearly 30% due to material shortages. The laboratory fell silent, except for the hum of equipment and the scratch of pencils on paper, as the team worked through the implications of their findings. Through the small window high on the laboratory wall, Yamamoto could see the skeletal frames of partially constructed warships in the arsenal's dry docks. Construction had slowed to a crawl as steel allocations were diverted to other priorities. The shipyard that had once employed 12,000 workers now struggled to maintain half that number. Men were being pulled away for military service faster than they could be replaced. And yet here, in this fragment of enemy metal, was evidence that the American industrial machine was operating without such constraints. Lieutenant Commander Ichiro Tanaka entered the laboratory carrying a leather portfolio stuffed with intelligence reports. Tanaka served as liaison between the Metallurgical Research Division and Naval Intelligence Headquarters. He was a career officer who had seen action in the China theater before being assigned to technical assessment duties. His face carried the weathered look of a man who had witnessed too much and slept too little. He spread several photographs across an adjacent table, aerial reconnaissance images of American port facilities on the west coast. The photographs showed something that made Yamamoto's stomach tighten. The images depicted shipyard after shipyard, each one larger than anything Japan possessed, each one operating at full capacity. Tanaka pointed to one particular image of the Kaiser shipyards in Richmond, California, where the Americans were constructing Liberty ships using mass production techniques. The intelligence summary attached to the photograph estimated that the Americans were completing one of these cargo vessels every 4 to 5 days. 4 to 5 days. The entire output of Japanese merchant ship construction for a month could be matched by a single American shipyard in less than 2 weeks. Tanaka then produced a thicker document, a translated copy of an American industrial production report that had been obtained through neutral channels. The numbers were almost incomprehensible. The United States was producing over 90,000 military aircraft per year. Their tank production exceeded 50,000 units annually. Steel production had reached 90 million tons per year compared to Japan's 7 million. The gap was not closing. It was widening with each passing month. Yamamoto returned his attention to the shell fragment. He performed a hardness test using a Rockwell hardness tester, carefully applying calibrated pressure to measure the metal's resistance to indentation. The reading came back at Rockwell C58, extraordinarily hard yet not brittle. Japanese armor-piercing shells typically measured around Rockwell C 52 to 54. That difference might seem small, but in the physics of armor penetration, it represented a massive advantage. A harder projectile could punch through thicker armor while maintaining structural integrity. The next test involved impact resistance. Yamamoto's team set up a drop-weight test apparatus, subjecting small samples cut from the fragment to repeated impacts. The metal absorbed the strikes without spalling or fragmenting, maintaining its structural coherence even under severe stress. By comparison, samples of Japanese armor plate tested under similar conditions showed microfracturing after fewer impacts. The Americans had somehow solved the fundamental metallurgical challenge of creating steel that was simultaneously hard enough to penetrate armor and tough enough not to shatter on impact. As the afternoon wore on, each test revealed another layer of American industrial sophistication. A chemical analysis showed precise control of sulfur and phosphorus content, impurities that could weaken steel if not carefully managed. The carbon content was optimized for maximum hardness without compromising ductility. Even the manufacturing marks on the fragment's surface told a story of advanced production techniques. The metal showed signs of having been forged using hydraulic presses capable of generating thousands of tons of force, creating a denser, more uniform structure than Japanese methods could achieve. Nakamura brought over another set of fragments, these recovered from a different engagement near Leyte Gulf. These pieces came from American naval rifle projectiles that had been fired from battleship main batteries, 16-inch guns capable of hurling shells, weighing over 1 ton across distances of more than 20 miles. Under examination, these fragments showed the same superior metallurgical characteristics. There was no variation in quality, no evidence of rushed production or material substitution. Every sample reflected the same exacting standards. The implications were staggering. The Americans were not just outproducing Japan, they were doing so while maintaining quality levels that Japanese industry, even operating under ideal conditions, struggled to match. This was not a question of technique or knowledge. Japanese metallurgists understood the principles of advanced steelmaking. What they lacked was the industrial infrastructure to implement those principles at scale. Japan's steel mills were smaller, older, and increasingly starved of raw materials. The electrical power required for advanced electric arc furnaces was being rationed. The skilled workforce was being depleted by military conscription. Yamamoto requested access to comparative production data from the Yawata Iron and Steel Works, Japan's largest steel producer. The reports made for grim reading. The facility's annual output had peaked at just over 2 million tons in 1941 and had been declining ever since. Repeated American aerial attacks had damaged critical infrastructure. The loss of shipping meant that iron ore and coking coal could not be reliably transported from overseas sources. Even when materials were available, the aging furnaces could not match the efficiency of modern American blast furnaces that could produce twice as much steel using the same amount of raw materials. Sato pulled out a technical manual he had acquired before the conflict, an American metallurgical engineering textbook from Carnegie Mellon University. The book described production techniques that Japanese industry could only dream of implementing. Continuous casting processes, precision temperature control systems, automated quality testing. These were not theoretical concepts, but standard practice in American steel mills. The technological gap had existed before the conflict began, and the years of fighting had only widened it. That evening, Yamamoto compiled his findings into a comprehensive report. He wrote with clinical precision, letting the data speak for itself. The shell fragments demonstrated superior hardness, toughness, and structural integrity. The manufacturing quality indicated an industrial system operating with ample resources and advanced capabilities. The testing protocols had been rigorous, and the results were unambiguous. Japanese armor protection, despite all the effort and expertise invested in its development, was facing projectiles it had never been designed to defeat. The report's conclusion was carefully worded but unmistakable. Current Japanese naval armor, while well-designed and properly manufactured according to domestic standards, could not reliably defeat American armor-piercing projectiles. The enemy's superiority in materials quality, combined with their advantage in fire control systems and overwhelming numerical superiority, meant that Japanese capital ships could not expect to prevail in surface engagements against American naval forces. This was not a question of courage or tactical skill. This was simple physics and chemistry, backed by an industrial capacity that Japan could not hope to match. Lieutenant Commander Tanaka read the report 3 times before speaking. His voice was quiet, almost a whisper. He mentioned that he had a cousin serving aboard the battleship Yamato, the Musashi's sister ship, and the pride of the combined fleet. The young man had written home about the ship's invincibility, about armor so thick that no enemy weapon could penetrate it, about guns so powerful they could decide the outcome of any battle. Tanaka wondered what he could possibly write in response. How could he explain that the entire premise was flawed, that the great battleship was less a war-winning weapon and more a monument to industrial ambitions that Japan's economy could never sustain? Yamamoto had no answer to offer. He thought about the men he knew who were serving in the fleet, skilled officers and dedicated sailors who believed they were fighting with the best equipment their nation could provide. They trusted that the armor surrounding them had been crafted with the finest materials and the most advanced techniques available. And in a sense, that was true. Japanese metallurgists had done excellent work within the constraints they faced. But those constraints were severe and getting worse. The Americans had no such limitations. They could afford to use the best materials, employ the most advanced processes, and reject any output that failed to meet exacting standards. They could build ships faster than they could be sunk and replace losses that would cripple Japan's fleet. Over the following weeks, additional fragments arrived at the laboratory from various engagements across the Pacific. Each batch told the same story. American ordnance quality remained consistently high, regardless of production date or manufacturing facility. Whether the shells came from projectiles made in Pennsylvania or California, whether they were produced in early 1943 or late 1944, the metallurgical quality never wavered. This spoke to a level of industrial standardization and quality control that was almost frightening in its implications. Yamamoto expanded his analysis to include fragments of American aircraft components, armor plate from destroyed tanks, and even structural steel from damaged vessels. Every sample reflected the same pattern: abundant resources, advanced manufacturing, rigorous quality control. The Americans were not cutting corners or accepting inferior materials. They were producing vast quantities of war material while maintaining standards that Japanese industry could rarely achieve, even in small batches. The psychological impact on Yamamoto's team was profound. These were men who had devoted their careers to advancing Japanese metallurgical science. They had believed that dedication and expertise could compensate for material limitations. They had convinced themselves that Japanese quality could triumph over American quantity. Now they held irrefutable evidence that the Americans possessed both quantity and quality in overwhelming measure. Nakamura began spending long hours reviewing pre-conflict industrial surveys, trying to understand how Japan's leadership could have so fundamentally misjudged the situation. The numbers had been available for anyone willing to look at them honestly. American steel production in 1941 had exceeded Japanese output by a factor of 12 to 1. American petroleum production was hundreds of times greater. American electrical generating capacity dwarfed Japan's entire grid. These were not military secrets, they were published statistics. Yet somehow the decision had been made to engage in conflict with a nation that held such overwhelming industrial advantages. The laboratory received a visit from a delegation of senior naval officers seeking to understand the implications of Yamamoto's findings. The group included a vice admiral who had commanded carrier forces in the early months of the conflict, when Japan had enjoyed tactical success. The admiral listened to Yamamoto's presentation with growing dismay. When the briefing concluded, he sat in silence for several minutes before asking a single question: how long had the Americans possessed this metallurgical advantage? Yamamoto's answer was devastating. Based on his analysis of the manufacturing techniques and the facilities required to implement them, the American advantage had existed for at least a decade, probably longer. The electric arc furnaces, the precision forging equipment, the quality control systems, these were not emergency wartime developments. They were the product of sustained industrial investment over many years. Japan had never possessed equivalent capabilities and, given current circumstances, never would. The admiral's response was barely audible. He mentioned that he had studied at the Naval Academy in Annapolis years before the conflict, had seen American industrial facilities during that time. He remembered being impressed by their scale, but had dismissed it as wasteful excess, inefficient compared to Japanese methods that prioritized quality over quantity. Now he understood that the Americans had achieved both scale and quality, that their apparent excess was actually a reserve capacity that could be mobilized when needed. Japan had built a military designed to win a short, decisive conflict. The Americans had built an industrial system capable of winning a long war of attrition. As winter approached and American forces continued their advance across the Pacific, Yamamoto's laboratory expanded its work to include defensive countermeasures. If Japanese armor could not reliably stop American projectiles, perhaps different armor arrangements or supplemental protection systems could improve survivability. The team experimented with various configurations: angled plate arrangements to deflect incoming fire, composite armor systems combining different metal layers, even desperate schemes involving concrete backing to absorb impact energy. The results were discouraging. Every modification that provided meaningful protection also added significant weight, reducing ship speed and maneuverability. The additional armor required more steel that Japan could not spare and consumed space needed for other critical systems. Moreover, even the best arrangements they could devise still could not guarantee protection against the heaviest American projectiles. The fundamental problem remained: The Americans could build guns powerful enough and shells hard enough to penetrate any practical thickness of armor. Sato proposed a different approach. If Japanese ships could not defeat American metallurgy, perhaps they should stop trying. He suggested abandoning the battleship concept entirely, focusing instead on smaller, faster vessels that relied on speed and evasion rather than armor protection. Submarines, destroyers, fast cruisers, these could potentially accomplish missions without requiring massive armor belts that consumed resources and provided illusory protection. The proposal was noted but never seriously considered. Too much had already been invested in the battleship program. Too much national prestige was tied to vessels like Yamato. Admitting that the entire concept was obsolete would require acknowledging that Japan's naval strategy had been fundamentally flawed from the beginning. Yamamoto continued documenting his findings with meticulous care. He understood that his work might be dismissed or ignored by those unwilling to accept its implications, but he also believed that someday, when the conflict ended, his research might help explain what had happened and why. He created detailed photographic records of every fragment, preserved samples of both American and Japanese metallurgy for future comparison, and maintained comprehensive test logs that would allow others to verify his conclusions. In March of 1945, Yamamoto received notification that the laboratory would be evacuated due to increased American aerial attacks on the Kure arsenal. The team was given 2 weeks to pack critical equipment and records before relocating to a facility in the mountains north of Hiroshima. As Yamamoto supervised the packing of his research materials, he reflected on how much had changed since that October morning when he had first examined the fragment from Musashi. The intervening months had brought a cascade of defeats. The combined fleet had been shattered at Leyte Gulf. The Americans had captured Iwo Jima and were preparing to assault Okinawa. American aircraft now ranged over Japan almost at will, destroying what remained of the industrial infrastructure that had once seemed so formidable. The battleship Yamato had been sent on a suicide mission, loaded with just enough fuel for a one-way voyage, and had been overwhelmed by American aircraft before reaching its target. The great ship had capsized and exploded, taking over 3,000 sailors to the bottom. Nakamura helped carry boxes of records to the trucks, waiting to transport them to the new location. He paused to look at the harbor where the remnants of the fleet lay moored. Several battleships and cruisers sat immobilized, unable to operate due to fuel shortages and mechanical problems. American submarines had so thoroughly disrupted shipping that petroleum products could barely reach Japan, let alone be distributed to naval vessels. Even if the ships could sortie, they would face American carrier task forces that had demonstrated the ability to overwhelm any surface fleet through sheer weight of numbers. The new laboratory location was far more primitive than the Kure facility. The building had previously served as a sake brewery and required extensive modifications to accommodate scientific equipment. Electrical power was unreliable, available only a few hours each day. Fresh metal samples for testing became increasingly difficult to obtain as the military situation deteriorated. But Yamamoto continued his work, driven by a sense that understanding the truth mattered, even when that truth was painful to confront. He began writing a comprehensive treatise on naval metallurgy, incorporating all his research findings. The work was partly technical reference and partly cautionary tale. He documented the evolution of armor and projectile development, explained the physical principles governing armor penetration, and provided detailed comparisons between Japanese and American metallurgical capabilities. But he also included sections on industrial planning, resource allocation, and the importance of honest assessment of one's own capabilities relative to potential adversaries. The treatise's most provocative section dealt with what Yamamoto called the illusion of qualitative superiority. He argued that Japan's military planning had been fatally undermined by the belief that superior spirit and technique could overcome material disadvantages. This belief had some basis in early conflicts against less industrialized opponents, but it had catastrophic consequences when applied to conflict with an advanced industrial power like the United States. The Americans had not needed to choose between quality and quantity. They had simply produced enormous quantities of high-quality material. Japanese planners had convinced themselves this was impossible, that mass production necessarily meant inferior products. The evidence proved otherwise. As summer arrived, Yamamoto received word that the conflict was approaching its end. The circumstances of that ending were almost unimaginable. American aircraft had deployed weapons of unprecedented destructive power, single projectiles that could destroy an entire city. The government had accepted surrender terms that would have been unthinkable months earlier. The Imperial Japanese Navy, once the third largest in the world, would cease to exist. The great battleships that had consumed so much of the nation's resources and so much of Yamamoto's professional energy would be broken up for scrap or used as targets by the victors. In the quiet days after the surrender, Yamamoto returned to the fragments that had started his investigation. He handled them carefully. These pieces of metal that had traveled so far and revealed so much, they represented more than just superior metallurgy. They were physical evidence of a society that had organized its entire industrial capacity for sustained conflict, that had mobilized resources on a scale Japan could never approach, that had married scientific knowledge to manufacturing capability in ways that produced overwhelming material advantage. He thought about all the engineers and metallurgists who had worked in similar laboratories throughout Japan, bright men who had done their best with limited resources and aging equipment. He thought about the factory workers who had put in impossibly long hours trying to meet production quotas, even as materials grew scarce and equipment broke down. He thought about the sailors who had trusted that their armor would protect them, who had gone to their deaths believing they had been given the best their nation could provide. In a sense, they had been. But the best Japan could provide was not nearly enough. Yamamoto's treatise on naval metallurgy was eventually published in 1948, after occupation authorities determined it contained no sensitive military information. The work became a standard reference in Japanese engineering education, valued both for its technical content and its unflinching analysis of industrial limitations. Several of Yamamoto's former colleagues went on to successful careers in the rebuilt steel industry, applying lessons learned during the conflict to peacetime manufacturing. Japan's post-conflict steel industry would eventually become one of the most efficient and technologically advanced in the world. But that transformation took decades and was built on honest recognition of previous shortcomings. Nakamura became a professor of materials science at Kyoto University, where he trained a generation of engineers in advanced metallurgical techniques. In his lectures, he would sometimes bring out one of the American shell fragments that Yamamoto had preserved, using it to illustrate the importance of quality control and the dangers of underestimating competitors. His students would examine the fragment's grain structure under microscopes, marveling at the precision of the manufacturing process, learning from an artifact of defeat how to build for the future. The larger lessons of Yamamoto's research took longer to absorb. Understanding that the conflict had been unwinnable from an industrial standpoint required confronting uncomfortable questions about leadership, planning, and the willingness to pursue courses of action despite contrary evidence. The metallurgical evidence was clear. Japan had engaged in sustained conflict with an opponent whose industrial capacity was an order of magnitude greater, whose access to resources was essentially unlimited, whose manufacturing quality matched or exceeded anything Japan could produce. This had not been a close contest, where superior strategy or courage might have changed the outcome. This had been a fundamental mismatch that no amount of tactical brilliance could overcome. In his later years, Yamamoto would sometimes take out his preserved samples and reflect on what they represented. These fragments had once been part of weapons designed to penetrate the most powerful armor Japan could manufacture. They had done exactly what they were designed to do, not through any exotic science or revolutionary technique, but through the straightforward application of abundant resources and advanced manufacturing capability. They were products of a system that could afford to do things properly, to use the best materials, to reject inferior output, to maintain standards even while producing at unprecedented scale. The fragments also represented something more personal. The moment when professional certainty gave way to uncomfortable truth, when expertise met evidence that could not be dismissed or explained away. Yamamoto had devoted his career to advancing Japanese metallurgical science. had believed that dedication and skill could overcome material constraints. The fragments proved otherwise. They demonstrated that some advantages could not be compensated for through effort alone, that industrial capacity mattered more than individual brilliance, that wars between modern nations were ultimately contests of production and resources. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.